Now
Thank you.
let's now let's welcome our invited speaker of the session, Dr. Shuvro Chowdhury. Hi, Shuvro.
Hi.
Dr. Shuvro Chowdhury received his PhD in electrical and computer engineering from Purdue University in 2022. His doctoral research focused on developing a general framework for mapping quantum problems into probabilistic networks, contributing to the foundation of probabilistic computing. He is currently a postdoc researcher at the OPUS lab, orchestrating physics for unconventional system lab at UC Santa Barbara. And his research interest spans probabilistic and quantum computing, machine learning, and the simulation and modeling of nanoelectronic devices. With that, let's welcome Dr. Chowdhury for his invited talk session. I'll set the timer.
Okay. Can you see my screen?
Yes. Maybe
Okay.
present. We're not seeing it in presenter mode.
Right. Yeah. Now it's all right?
Yes. Now it's good.
Oh, okay. Thank you very much. Hello. So can I start?
Yes, please.
Oh, okay. Yeah. So welcome everyone. I'm Shuvro Chowdhury from University of California, Santa Barbara. I work with I'm a postdoctoral scholar there, and I work with Professor Kerem Chamsari. Today's my talk's title is is pushing the boundary of quantum advantage with probabilistic computers, and welcome you all to my talk. I hope you will enjoy this. So before I begin, I want to sincerely thank all my collaborators, and as you can see, it's a long list of collaborators across the globe. Anyway, so let's dig in. So the title says that we are talking about probabilistic computers. So before I introduce the probabilistic computer, I want to introduce its basic building block, which we call a probabilistic bit, or in short, we call it p-bit. So what is a p-bit? A p-bit, we ideally view p-bit as a three-terminal device, and it's a building block of the probabilistic computer. So a p-bit has a real valued input and a two valued output. So and here I'm showing a binary output, but it also applies for, I'm showing a bipolar output, but it equally applies for binary outputs as well. Just you have a two valued output. Okay, so this p-bit and the third terminal is the power terminal. So that's how it is a three-terminal device. Now, the ideal characteristics of a p-bit is something like this. So let me explain this a little bit. So if you apply a little bit negative input, so depending on your device, it might by different quantity, voltage or current or something else. But if the input is negative, then so input is if the input is negative. So if the input is negative, then what will happen is that the p-bit will try to spend more time in the -1 state rather than the +1 state. Now, so if you see the average behavior of the p-bit output, you will see a negative quantity, something like this. Now, if you apply zero input, then there is no preference for the p-bit to choose one state more than the other. So it will spend equal amount of time in the both +1 and -1 states. So over the if you see the average response of this p-bit, then you will see a zero average. Now, what you can do is the opposite. You can apply a positive input, and if you apply a positive input, then what happens is that it will go behave the opposite way. Like it will spend more time in the +1 state and less time in the -1 state, and on average you will see a positive behavior, positive output. So this is how we view the ideal behavior of a p-bit is, and we can mathematically formulate this p-bit behavior by this equation. And this is a well-known equation in machine learning and other fields of science and technology. And in the machine learning field, it is well known as binary stochastic neuron. But what we are kind of like advocating is the hardware form for this, not the ideal mathematical thing. So how can you build this type of device, this behavior in hardware? So over the years, we have seen many ways to do this in hardware. For example, you can build this behavior with magnetic tunnel junction based device. There are various implementation with diodes. We can use pure digital CMOS or mixed signal CMOS. So there are various ways, and every day I kind of like get to review various device proposals for PIVT. So this is kind of like brief introduction for your PIVT, what a PIVT is. Now okay, so now let's talk about the anatomy of a probabilistic computer, like how a probabilistic computer works. So in order to solve any important problem, you need actually, you cannot just do it with one pivot. So you need actually many pivots. And when you have many pivots, you need to somehow figure out how to make them interact with each other to solve any important problem. So in this case, the simplest way to build a probabilistic computer is to apply pivots, use pivots and interconnect them with this equation. Now, so what happens here is that a given pivot will collect the state of its neighbors, and then apply this equation to figure out what is its input, and based on this input, it will figure out its response accordingly. Now, so this is the two equations that are needed to build a probabilistic computer. And once you have these two equations, you have enough. You don't need anything. But one more thing that I want to mention is that what is the ideal behavior that we expect from a probabilistic computer, given you have built a computer with these two equations. So these results, this is also something known, which is like Boltzmann law. So if you build a P computer with just these two equations, it will ideally follow this Boltzmann law. The Boltzmann law says that given a state of the pivot, you can find its probability by taking the exponential of its the state's corresponding energy, which is given by this. This is the energy equation for a given state. Now, this equation is also very well known in the field of this optimization and magnetic materials or any other fields, like many other fields. So this is well known as the classical Ising equation, right? So this equation so this is the expected behavior of a probabilistic computer if you are able to build it properly. Another point is like this Ising equation is not necessary to build a probabilistic computer, or it is not a limiting factor for the PBIT. The PBIT equation is different, is applicable for many other equations. So you can define any other energy function, but what will happen is that you have to change your the second equation accordingly to match with your energy expression. So here it is an Ising expression with the second order interaction. You can have, for example, an extension of third order energy function, and then you have to kind of like accordingly take into account those third order interaction here. So that's it. Now, our vision is to build a probabilistic computer with an asynchronous architecture where each pbit will update according to their own will, and then the pbit which is computing its response will collect the response from its neighboring pbits, apply this equation, and kind of like generate its own response. So it's kind of like asynchronous, like each pbit is not dependent on any particular clock. They are kind of like updating on their own will. So like much like a physics of nature, like right in a for example, the particles in a gas container. So each molecule is like doing whatever they want to do and interacting with their neighbors at their own will. So that is kind of like our ultimate vision to P computer to look what to a P computer to look like. Now, the final thing is like how do you build a synapse? So similarly, you have like the pbits, you have kind of like various options for building synapse. Like you can do like analog crossbar arrays, or use memory stores, or even you can do it with digital CMOS in memory compute. So there are also various choices for your building your synapse, and this and yeah, so that depends on your need and your requirements, what you want to achieve, and what are your limiting factors. Based on this, you can choose any of the items I mentioned here. So now let's talk about the state of the art probabilistic computers. Where are we now? So it all started with the demonstration of a 8 pbit device, so which is like a proof of concept in 2019, where we showed that we can build a probabilistic computer with a nanomagnet based device as a p-bit, and we solved a factorization problem with 10 bits. But nowadays, after a lot of research, we are now at least have shown working example with all digital logic up to 10,000 p-bits, and we have been able to solve like a 32-bit factorization example, for example. This is not compared to what people in the computer science usually do. They are kind of like doing many more numbers, but you can see that what is the compared to the community, we are kind of like way up there. And in our very latest example, we have been able to go up to 40-bit factorization. And I'm not showing here our latest result. So, but in our latest result, we have been able to go up to 1 million p-bits. But that is under kind of like publication. So we are not. I'm not showing it this here. So we have been with all digital logic, we have been able to go up to 1 million p-bits. So this is kind of like the state of the art probabilistic computer. Where are we now? Now, over the years, we have found many applications of p-computing or p-computer. So one of the first obvious example or application is combinatorial optimization. You have a optimization problem, and you replace this problem variables with p-bits, and then you apply your optimization algorithm to get to the correct ground state of the problem. So that's basically the optimization problem with probabilistic computer. And here I am giving some reference from our recent works from our group. And then the other application domain is this generation of massive parallel number. P-bits are ideally suited for this. Each p-bit without any input, as I showed before, behaves like a perfect random number generator. So you can gather many of them as much as you want and kind of like generate random numbers. Now you can also apply this p-bit into machine learning and AI field. You can use them to train infer from belief networks and energy-based Ising models. Also some reference from our recent work from our group. And finally, I want to include this other application, which is very interesting, that we can use p-bits to solve some problems of quantum domain. Not all of them, because p-bits are not quantum. They are kind of like still classical. So they are not expected to replace qubit, but still we can solve a certain class of quantum problems also. So there are two ways of solving this problem. One is kind of like the traditional way of using quantum Monte Carlo, and then the other most recent way of doing it with neural networks. So yeah, also there are some recent reference there. I think I'm running behind of time. Okay, anyway. So now let us talk about some real example that we have worked on from our group. So the first example is an optimization example, and we will be talking about 3D spin glass. So recently a paper came out from DWeb and published in Nature, where they were solving a 3D Ising spin glass problem on a cubic lattice, and they are basically trying to solve this classical Ising Ising Hamiltonian for this 3D spin glass. And they kind of like showed that when they applied their quantum annealer to solve this problem, they kind of like get better result from the traditional annealing algorithms, which is like simulated annealing and simulated quantum annealing. So in this plot, I'm showing on the y-axis is this final residual energy, which is kind of like a measure of how far you are from the true ground state energy. And on the x-axis, I'm showing the annealing time. So this annealing time, so we know that if we increase the annealing time, we will get better and better results. So this the slope of this curve is important, which kind of like tells you like how fast you go to the ground state given an algorithm. And they kind of like measured this slope for these three types of annealing algorithm, and they were kind of like bragging about that their slope is the higher compared to other annealing based algorithms. So that was very interesting to us, because it was after all, it was a classical optimization problems. So, and it was not immediately obvious like why you would need a quantum annealer for this problem. So we kind of like took a version of simulated quantum annealing. We call it DT-SQ, I mean discrete time simulated quantum annealing, where we have physical replicas of the same problem, and these replicas interact with each other. And then since we have p bits which are very cheap, and we can physically lay out these replicas in a single chip, so we also take the best result out of this annealing, after this annealing, and we see that there is a change in slope with the number of replicas. This R is the number of replicas we use, and we see that okay, so we see that when we change the replicas gradually, the slope also increases gradually, and around 2800 replicas we get to match the slope of the quantum annealer that was reported here in the previous paper. And then it was we had a kind of like theory with the extreme value theory, with which we are able to explain the behavior of this curve, and which is like almost getting there. So and then the other problem with this thing is like this number of replicas required to match the quantum annealer is huge. So it was a question like, is it really possible to implement this many spins in a real hardware? So that's why we collaborated with CMU, and they kind of like did the feasibility analysis for us, and they kind of like showed us that yes, with modern technology, fabrication technology, you should be able to include this many replicas of the same problem, which is this size, like around 2700 spins per replica, and then you have this many replicas in a single chip with modern technology. So, and you can see that the slope is actually very similar to what DOF reported. So the take away message from this thing is like that you do not need actually quantum annealer or quantum computing to get quantum annealer like performance. You can just do it with modern chips, like today with modern fabrication technology. Okay, so we also did we also kind of like applied advanced algorithm for this 3D spin glass problem. So for spin glass type problem, the gold standard classical algorithm is this parallel tempering, and we are using a variant of this which we call adaptive parallel tempering, and we are also applying iso energy cluster moves to enhance the power of the parallel tempering algorithm. So we applied this, and we see that this parallel tempering algorithm performs actually better. Initially it is a little bit slow, but after a certain point it sharply decreases the residual energy. And we kind of like studied this behavior across different sizes, and we see that this is a kind of like repeatable behavior. So this is a collapse curve. So for collapse curve over like various sizes, and all of them kind of like show the similar behavior. So it's a kind of like general pattern of this algorithm. So initially it has a slope of 0.5, but then after a certain point it goes very sharp with a slope of minus 1.5. So this new algorithm also I should not say new, it is a state of the art algorithm, also gives you better performance compared to the annealing algorithms we have used before. And finally we also check the architectural improvements. So here I am showing on the left is like, say, let's say I have a target residual energy to achieve, and I am kind of like showing the minimum number of Monte Carlo samples needed to achieve this target residual energy over size of the problem. And then in the middle I am showing this number time to perform a single MCS versus size. So in traditional general purpose computer, CPU or GPU, this time will increase with the size. But in our system, since we can physically lay out the spins, this time is constant. So that's the kind of like order of n improvement over the general purpose computers. And then if from these two curves, you can estimate the total number of time, total time to kind of like achieve this target residual energy using various computing platforms. Like the top one is CPU, and then there is a order of n improvement with FPGA based P computing. And then if you really want more savings, then you can build this P computer with nano devices, and then you will get another factor of order of 2 improvement in prefactor, just speed, not speed up, scaling. So this scaling improvement is also possible. So with P computer. So next, I will probably touch this thing very quickly, this quantum simulation. So this is a legitimate quantum application. So I am now solving a proper quantum problem. So this is also a DOA paper from a little bit earlier. So there I'm showing a 2D qubit lattice there, and then I am applying transverse field Ising Hamiltonian to on this qubit lattice, and I am observing a particular order parameter and its relaxation. So I am starting from a very particular state of this cubic lattice, and then I'm applying this Hamiltonian, and I am kind of letting it go, and then I am seeing, like, after which time it start to relax, it equilibrates. So this is my equilibrium value, and this is the time I need to equilibrate. So then in this paper, the DOF claimed that they have a 3 million x improvement over classical optimized algorithm for this problem. And then we kind of like come in and we kind of like used our probabilistic computer to challenge this somewhat. Like it's not, yeah, we are not a probabilistic quantum computer, we do not have qubits, but so we wanted to see like what we can do. So it was a fun project. So we applied this our P computing algorithm with on FPGA, and we immediately saw a 1000x speed up over this optimized CPU algorithm. And then we went ahead and kind of like did a P computing position with nano devices, based on the nano devices with magnetic tunnel junctions. And it's a projection. We kind of like really did some small scale problem with the SPICE, and from that we projected that this will happen. So we found kind of like that from FPGA to this nanomagnet based computer, we can get another 400x speed up. So overall, we kind of like finally, when we ended the project, we were kind of like short of like on the order of gap. So we started with a 3 million x improvement from CPU to quantum computer, and we kind of like bring it down to only just 10x. So, and we were getting all of these thing like at a room temperature and with much power than the D-wave computer, because you know that the quantum computer needs to use cryogenic temperature, and it needs much higher energy. But our system is like on FPGA and on a room temperature device, so it's like takes much less. So finally, I would give you the last application, which is like the machine learning side. So this is another fun thing. So this is like a 1D qubit chain with periodically bounded chain, and the goal is to kind of find the ground state of this system. So this is also a quantum system. So I am applying this again, this transverse field Ising Hamiltonian, and my goal is to kind of like get to the ground state of this Hamiltonian. So usually what people will do is people will use a machine learning model, which is like restricted Boltzmann machine. So they will have a layer of visible layers, and there is a hidden layer, and then they will use this model to kind of like learn the ground state of the system. So here what we have done is like we applied a restricted version, even further restricted version of this, where in traditional RBM we have kind of like one visible node is connected to all other nodes in the hidden layer. But in our case, we are applying a model where it is a limited connectivity. So it's not connected to all of them, all of the hidden layers. It's a limited connected. And in this particular example, I am using 5 connections. So each visible node is connected to 5 hidden nodes, is neighbors. And using this model and using the other machine learning techniques, we have been able to solve up to like 5,000 qubit. Like we went to the ground state of a 5,000 qubit problem, and you can see that we can get to like very close to the correct ground state, and we were able to go to this chemical accuracy level, which is like within 16e minus 4 accuracy level with compared to the ground state. So even with this sparsity and all of this, the probabilistic computer was able to give you very standard results. So finally, I'll probably take 1 or 2 minutes. So this is my last slide, which is like this outlook and where are we going. So this is kind of like the technology roadmap, like where is the P computer is going. So P computer is supposed to work with like in a hybrid setup with CPU, and this probabilistic computer has, as I said in the beginning, like there are many ways to do this thing. So you can use CPU to emulate a probabilistic computer. You can use GPU, you can use FPGA, and then you can use like this nano device based P computer. Each has its own pros, advantages, and challenges. So if it is CPU on the very one extreme, you can use CPU. So it is very easy to emulate, but then its performance is a little bit restricted. But on the other extreme, you can use very sophisticated nano device based device. Performance will be very high, but then there is a challenge of how to synthesize these devices and kind of like make these things work, how to fabricate them. So this is kind of like your roadmap technology. And then I'm showing that how you can to show this power consumption versus throughput comparison for a single so with all these other devices that we have, like with GPUs, TPUs, and compared to our devices, and we can see that when we solve the same problem, all the devices I'm listing on the right, they are used to solve the same problem, and you can see that our performance, power consumption is very low compared, and our sampling throughput is also very high. And whatever I said before is that like we have already experimental evidence showing that nanomagnetic based device can show nanosecond based fluctuation, and already been demonstrated by various groups around the world. And if we use those type of device, very fast fluctuation device, then right now our all digital device consumes kind of like around 30 to 35 or 40 watts. But then using this 1 million of such qubits, it will take, and using those devices, it will take only around 20 watts. We project based on our projection, it will take only project. So there is a huge improvement both in sampling throughput and in power to gain if you use this monolithic based devices, P computers. So thank you. That's all. And if you have any questions, I'll be glad to have them.
Thank you so much, Shuvro. Do we have any questions from the chat, or if you want to ask a question, you can raise hand. Okay, if not, I want to ask some questions.
Everyone is very tired.
Yeah, this is our last talk of the whole 4-hour. Yeah,
it's not very easy to come in last.
Yeah, but it's great. It's the most, I'm sure it'll be the most memorable one because it's the last one. Yeah. So it's very, very cool work, and it sounds very exciting too that we see these great improvements for like, I guess, like next generation of computing hardware. So I was thinking, like, when you mentioned, like when you do quantum simulation, essentially it's not really a quantum simulation, right? It's just
No.
I see. It's like varying.
I am emulating a quantum system. So what is happening there is like I kind of omitted some details for the sake of time. So for the quantum system has really kind of like for example, it has 10 qubits, for example, in the qubit lattice. But then in order to emulate this with classical p-bits, you need to have many, many replicas of the same system. So for example, in this case, I am using 10 replicas. So if you have 10 qubits originally, you need 100 p-bits to emulate that. So that's the price you pay, like for not being qubit. But then the idea is like qubits are expensive and complex to fabricate, but then p-bit is very cheap and kind of like easy to build. And you gain something from room temperature operation and power consumption. So that's the motivation.
I see. Yeah. So I do know that like physically qubit and p-bit, they're different, right? Like they,
Definitely.
yes. So it seems like this only applies to a subset of quantum problem, like you also mentioned.
Exactly.
What kind of quantum problem that you think are suitable to put for a p-bit to solve instead of using like a qubit?
So yeah, in that field, the people who do these quantum simulations, they kind of like know this already. So this is kind of like they call it like a subset of problems is known as stochastic problem, not stochastic, stochastic. So this class of problems, so they are so what happens, what is the actual problem is like sometimes you have a problem when you try to solve this with qubits. The probability, like all the Monte Carlo samples, Monte Carlo algorithms use probabilities, right, to generate to move from one sample to another based on probabilities. But then sometimes when you map this quantum thing into this classical thing, the probabilities can appear negative. And when the probability is itself negative, then Monte Carlo algorithms fail because they don't know what to do. Negative probability is not kind of like defined in a traditional sense. So if some quantum problem has this negative probabilities in the mapping, then those problems will not be applicable for p-bit simulation. So you have to be restricted space in the positive family. So that type of problem is called stochastic.
I see. Thank you.
Yeah.
All right. Do you have any more questions?
I did not see. Oh no, I don't see anything.
Yeah. If not, then let's conclude our session and let's give a round of applause to all the speakers of the session.
Thank you.
And we have one more thing, which is the poster session that's hosting at GatherTown. So the Zoom part of our conference is pretty much done now. Please head over to the GatherTown. If someone sent the GatherTown link, let's see.
Yeah, I have the GatherTown link.
Yes. Yeah, you can go ahead and
Okay.
explore the poster and also like vote your favorite poster and your favorite meme or art. And we will have a closing session towards the end at GatherTown. Yes.
All right. Okay.
All right. Thank you so much.
Thank you.